In this lesson, we're going to continue to look at bonding, but now we're going to move from the single bonding we did in the last lesson to double bonding. All right, so this is the problem we're going to work on. Okay, I'm recording this. I know you guys have already done it, so anyway. Then here's your electron dot formulas becoming sharing arrangements, and finally Lewis dot. And then finally we get to this shape for the three-dimensional shape. And so the question was, well, how did we get to that? All right, well, the sulfur and the chlorine too, for that matter, started out with an sp3 hybridization. Okay, this is sp3 hybridization. That's what we showed you on Friday when we first did this. And so you've got four single balloon sort of shapes, equidistant, equally spaced. Okay, 109.5 degrees is the distance between the axis between each of these balloons. Okay, 109.5 degrees. In order to bond, then you take the one electron that's in one of the sulfur orbitals here. There's one electron here, and one electron that's in another sulfur valence orbital down here, and you share those to make this kind of wiener-shaped bond. The other two orbitals over here, these two over here, those already have a pair of electrons and a pair of electrons. Okay, so they don't need to bond with anything. They've already got the two electrons they need, all right, to be full. That makes sense? All right, so hydrogen, remember, only has an s orbital. So the s orbital is spherical. There's just one electron there. So when bonding occurs, those two orbitals, the one from the hydrogen and the one from the sulfur, they're going to combine together. All right, they're going to make one into that cigar shape. All right, I kind of didn't draw this low enough to show you the chlorine, but the chlorine has this same shape, and so the unhybridized orbital from the chlorine, I'm sorry, the hybridized orbital from the chlorine with only one electron is going to share up here as well. Okay, maybe I can show part of it. Maybe do like this, and I'll put the chlorine here and just show one orbital down here. Okay. So one orbital from the chlorine, one electron there. Those two orbitals are going to combine together to make this orbital. Does that make sense? Does that help you out? Think you got the rest of it figured out? Yeah. All right. Any other questions? What other questions do you have? Now's the time to ask, because I move it on to something else, and I want to make sure you got this pretty clear before we do move on. Okay? All right. Okay, so our first look at things was to write the electron dot to the Lewis dot formula for this thing here, which as far as I know doesn't really exist, but it's a good way to practice. Okay, it's hydrogen, sulfur, chlorine, hydrogen, sulfur, chloride, I suppose is what we call that. Then show the shape of the valence orbitals and bonds. Here's our Lewis, this is our electron dot formula for hydrogen, electron dot formula for sulfur, electron dot formula for chlorine. We want to combine those in such a way that the hydrogen gets 2 electrons, that fills up its valence level. Sulfur gets 8 electrons, that fills up its valence level. Chlorine gets 8 electrons, fills up its valence level. So most atoms want to have 8 electrons like the sulfur and the chlorine. Hence we get this something called the octet rule. And so what we end up with is this Lewis dot formula that looks like this. And then I was just pointing out here that both this sharing of 2 electrons and this sharing of 2 electrons between atoms is called a single bond. Single bonds are the sharing of 2 electrons. Then if we're drawing out the shape of the valence orbitals and bonds, this is what we get. Okay? And pointing out also that this is a sp3 hybrid because we hybridized all 4 orbitals. Okay? This is an sp3 hybrid because we hybridized all 4 orbitals. Technically, hydrogen's hybridized. We just don't call it anything because, you know, its hybridization doesn't really help us much. Okay, knowing that doesn't really help us much. So sp3 hybridization, and then these are single bonds because inside this cigar shape or wiener shape are 2 electrons. Okay, I could put in the electrons. I could draw in that double arrow thing like we do in orbital notation. Okay, single bonds are always sigma bonds. We're going to find out that not all bonds are sigma bonds, but single bonds are always sigma bonds. Okay, so now we're going to do this. write the electron dot to Lewis dot formula for a combination of this thing here. This is called formaldehyde. Then draw the shape of the valence orbitals and bonds. So I put down the electron dot formulas first, and I'm going to share one time between each of these atoms and then see what else I can do. Okay, so I can share these two right here, and that gives that hydrogen the 2 electrons it wants to have. I'm going to share these two right here. That gives this hydrogen the 2 electrons it wants to have. Carbon now has 6. If I share 1 electron between carbon and oxygen, now I've got carbon with 7 and oxygen with 7 electrons. But they both want 8. They're not done until they get 8. So we're going to share 1 more. So now we're getting into something called a double bond. Okay? These are single bonds because we're sharing 2 electrons. Now we're sharing 4. That's called a double bond. Okay? All right. We're going to put that together then into the Lewis dot formula. And what we do with the Lewis dot formula is squeeze the electrons in between the 2 atom symbols. Okay? And we get this. Here's our carbon. Here's 2 electrons squeezed between hydrogen and carbon. So it's kind of like we squeeze it together and they kind of squish side to side, if that makes any sense to you. And these 2 squish side to side over here. Could have put this hydrogen on the bottom. Nothing special about putting it on the left. That is probably better if I didn't put it either one of those 2 places. I put them in a different angle, but we don't worry about that now. So in between the carbon and the oxygen, I need 4 electrons. When I'm doing the Lewis dot formula for a combination like this, where I have 4 electrons, I make it in this sort of 4 corners of a box arrangement. Okay? And then we put the oxygen over here, and there's 2 electrons that aren't combined, 2 pairs of electrons that aren't combined with anything. We have to keep those. Can't just get rid of them. So that's our Lewis dot formula then for this combination of atoms. And we have single bonds here and here, and we have a double bond here, and just for the record, we have lone pairs of electrons here and here. Okay? Just some terminology. All right? Any questions about that so far? Then, what I want to do now is to figure out what the shapes are going to be. So we're going to have a completely new kind of shape for bonds now. Okay, let's start with this one right here, the double bond. So you can either draw a dot. Let's move everything from just doing the dots for the nucleus, which we were doing when we're doing just atoms and their electron energy levels and so forth. Let's go ahead and put in a small carbon here for the nucleus of the carbon, and a small oxygen here for the nucleus of the oxygen. Okay? All right. Remember, or recall, when we're talking about the reason why electrons exist in orbitals is that you can only get 2 electrons in the same region. Okay? Now remember what we said was that electrons have a negative charge. When they're moving around, and within the electron clouds, they're moving around really, really fast, close to the speed of light. When they're moving around, the movement of those electrons creates a magnetic field. So if it's moving in the direction of my right thumb, the electromagnetic field is in the direction of my right hand fingers. Okay? And so if I spin 1 electron in one direction and spin an electron in the other direction, they can cancel out the electromagnetic repulsion. I get 2 electrons in the same space, and by that I mean the same orbital, but I can't get more than 2 in the same orbital, right? All right. So bonds are the same thing in that respect. I can't get 4 electrons in the same space. I can only get 2 electrons in the same space. Bonds, covalent bonds, are the sharing of orbitals. So we're overlapping, sharing, combining 2 orbitals together. So the rules about getting 2 electrons, only 2 electrons in an orbital, apply to only 2 electrons in a bond. Okay? Because I can only have 2 opposite spins. So once I cancel out the electromagnetic repulsion for 2 electrons, any other electrons have to be in some other space. You with me? Now, the nuclei here have protons. It's keeping that charge of opposite charge. Protons are positive, electrons are negative. That opposite charge is kind of keeping those electrons trapped in here, but the electrons, the pairs of electrons need to be in separate spaces within that trapped region. Okay? So here's what happens when I have a double bond. First of all, we're going to have that single bond shape, that sigma bond shape for one of those two bonds. Okay, let's put that in there. Here's the first of the two bonds right here. Okay, and there are two electrons in here. So I'm going to go ahead and put a pair of arrows like we did when we did orbital notation, just to show it. Okay, just to show it. Now, the other two electrons here in this Lewis dot formula shape I have, those other two electrons have to be between the carbon and the oxygen, but not in that same space. Okay? And so for that, something kind of weird happens here. It might seem kind of weird to you. Let's go back to what we were talking about when we first started talking about orbitals. And we said that p orbitals had what kind of shape? Double balloon. Okay, so let's put a double balloon shape here on this carbon and a double balloon shape on this oxygen here. Okay, so what's going to happen is we're going to have two orbitals that are not hybridized. When we were doing all these other orbitals up to now, we hybridized all four valence orbitals. Now we're going to have two orbitals that are not going to be hybridized. They're going to retain that double balloon shape, not the single balloon shape. Okay, so what happens is they basically reach out and touch each other around the wiener or hot dog shape or cigar shape or whatever. Okay, so this is like the hot dog, this is like the bun. Yeah.
How can you do that if you have two hydrogens?
The hydrogens don't double bond. The hydrogens single bond.
But you need two of them because you have.
Yeah. I'll show you in a second. Let's just do the double bond first, okay? All right. So I'm going to color code this one orange. Not that it matters what color it is, but basically what you're going to have is a double bond, a second bond, not a double bond. This is the second of the two bonds in a double bond. Okay? Got that? And this is not called sigma. So we said earlier that these single bonds are called sigma. Any bond directly on the line, it's called an axis. I like to call it a line. Any bond directly on and surrounding the axis or line between the two nuclei of two atoms is called a sigma bond. So this is a sigma bond, okay? But now we've got a different kind of bond entirely. This is called a pi bond. Now remember, these two parts, let's just look at the carbon for a second. These two parts of this p orbital, that's the same p orbital, right? We got two balloons making up a single p orbital. And the same here with the oxygen. Two parts of the same p orbital. So these are two antinodes. These are also two antinodes of a bond. Okay? So this is a part of the pi bond. This is also part of the pi bond. We're going to call this pi. Okay, so this is a pi bond. It's the same pi bond, not two separate pi bonds. I know that's hard to understand. And as much as I try to emphasize it in class when we're talking about it, as much as we go over it in class, somebody on a test, it happens every time, as hard as I work at this, somebody's going to say that's two different bonds. It's not. Okay, you with me? Okay, a pi bond has two parts. Say it with me. A pi bond has two parts. Y'all didn't say it very well. Come on, y'all can do better than that. Come on, guys. Come on. A pi bond has two parts. Maybe we'll get it this time. Maybe this time we won't anybody miss it on the test, okay? Got it?
Got it.
All right, now, the oxygen over here has two lone pairs of electrons. Well, those are hybridized orbitals. They haven't changed their shape from the hybrid shape. So we're going to have a single balloon shape that's kind of coming out toward you here, and a single balloon shape that's back behind. Okay? Now what that's doing is it's getting the pair of electrons in this hybridized orbital. I'll go ahead and draw in that double arrow shape like we did with orbital notation. Okay? As far apart as I can get from this one and these two, these two as far apart from these two as I can, and as for both of these as far apart as I can from all of these. Okay? So we no longer have 109.5 degrees separating it. Okay? All of these angles for the electrons, two electrons here, two electrons here, two electrons here, two electrons here, and so forth. All these are 109.5 degrees apart from each other, roughly speaking. Okay? These are now not 109.5 degrees anymore. This is 120 degrees apart. Okay? Because three things as far apart as I can get is 120 degrees. That makes sense? All right. Now, as far as the hydrogen to carbon bond, what we need here is a sigma bond that's kind of swinging out toward you and a sigma bond going back behind everything. Okay? So we kind of draw it in front and back like this, only with a bond. So let's see, I'm going to put one bond swinging out toward me like this. Not that you have to be, you know, an artist doing this stuff, but I'm just trying to help you see the perspective here. And there's our hydrogen nucleus sitting out here. Right? And then we're going to have one that's going back at an angle kind of away from it there. All right. The perspective makes sense to you? All right. So we need to go back to orbital notation to see what's happening with the hybridization. Okay? Got to go back to orbital notation now to see what's happening with the hybridization. Yep. So let's take a look at the carbon here. All right, here's a carbon. The original unhybridized set of orbitals for carbon look like this. You had 1s, then we had 2s, and then we had 2p. Okay. To hybridize this sp3, remember these are sp3 hybrids here and here. To hybridize this in sp3, we're going to hybridize all four of these orbitals, right? That's what we did. Everybody remember doing that? Okay, so we put them all together into a single set of four orbitals, right? And that's how we're able to bond 4 times for carbon. All right, now we're not going to hybridize all 4. We're going to leave one of these orbitals unhybridized so that we can keep this p orbital to form this pi bond. Does that make sense? So here's how we're going to imagine that happening. Okay. This time, we're only going to hybridize 3 orbitals. These 3 right here. Okay. Okay. And you don't hybridize hybridize this p orbital here. I'll have to fix that and make it look like a B here in a second once this dries. Okay. All right. So what we're going to do is have a carbon now. The 1s doesn't change. Okay. It's only those electrons in the valence level that do any bonding. So we don't really worry about what's in the lower energy levels. Okay. In this case, the only lower energy level is 1. Our valence electrons are in the second primary energy level. That's where that coefficient 2 comes from. We're going to combine 3 of these orbitals. 1, 2, 3. And we're going to leave 1 p orbital unhybridized. So it's going to be broken out by itself. Okay? So our 2 electrons in 1s will stay there. All right? This now is in the second primary level. It's 2p. It didn't change. It's still a 2p orbital. But these right here are going to be hybridized. Now, when we're hybridizing 4 orbitals, we call it sp3 because we hybridized 1s and 3 p's. So using that same idea, what are we going to call this? sp2. There you go. So this is it's an sp2 hybrid. Okay, our set of hybrids. And it's in the second primary level, so we're going to call it 2 for the primary energy level, sp2. Got that? All right. Now we've got a p orbital that's not hybridized, so we can do a pi bond. You got that? Now all 4 of these electrons are spread out over all 4 orbitals, just like with sp3. Okay? So now we have an electron in 2p in order to do this pi bond. We've got 1 electron in each of the hybridized orbitals to do 3 sigma bonds. 1, 2, 3. You see what I'm saying? So remember, any bond that's directly in a line between the nuclei of 2 atoms is a sigma bond. So this is a sigma bond, and this is a sigma bond. Okay? So add something else to our toolbox of knowledge. All sigma bonds stem from hybrid orbitals. Okay? These 2 lone pairs over here on the oxygen are also going to come from hybrid orbitals. All 4 of the orbitals for this drawing here were hybridized orbitals. So these lone pairs up here, those all came from hybrid orbitals. It turns out that all lone pairs of electrons stem from hybrid orbitals. Okay? So you can actually count the number of lone pairs and bonds to figure out what the hybridization is going to be. With this sulfur here, I have 2 lone pairs, 2 bonds. That's a total of 4 there. You could also say 2 lone pairs and 2 sigma bonds, or 2 single bonds. That's going to be an sp3 hybridization. Okay? With this one, 2 lone pairs and 1 bond, 2 lone pairs and 1 bond, that's sp2 hybridization. This is 3 bonds. That's sp2 hybridization. Okay? I can count the number of bonds pretty much and tell what kind of hybridization I have. That makes sense? There are some exceptions for some odd things that come along from time to time. Got it? All right, now we've got unhybridized P to do a pi bond and 3 hybridized orbitals to do these sigma bonds and lone pairs. Got that? Any questions? You want to do one for yourself now, see how you do? And in groups? All right, let's do this. Let's write the electron dot to Lewis dot formula. Okay. I'm just going to, it's the same instructions. I'm just going to give you a different molecule. You with me? All right. Let's do let's do C2H6. C2H6. This is called ethane. Ethene. Ethene. Not that you need to know that now. You need to know it in the next unit. But this is ethene. Okay? See what? That's not right. I apologize. H4 is what I want, not H6. That would be ethane. What I have here is ethane. I want you to do ethene. Okay? H4. C2H4. Now I was going to fix this. Okay, and when that dries, where's my pen? I can just use the pen. Or pencil maybe. Alright. And for those of you watching at home, let's see. Probably need to, I'll do the Lewis dots on this page and I'll go to another page for the remainder of this. Carbon has 4 electron dots, and I got 2 carbons, and I have 4 hydrogens. Not that it matters where you put the hydrogens. I'm putting them here because I kind of already know where we're going. You might start out with them someplace else, and that's okay, as long as you combine everything in the correct manner. And there's only one way to put this together with 2 carbons and 4 hydrogens. So we're going to combine or share 2 electrons. That gives hydrogen all the electrons it can stand. And I'll put 2 here, and I'll share 2 here, and 2 here, okay? And that leaves us a double set between the carbons, okay? So that's our electron dot formula going to the sharing arrangement, and then we'll go to the Lewis dot formula. So between the 2 carbons, I've got a double set of electrons, okay? And then I'm sharing 2 electrons with this hydrogen, 2 with this one, 2 with this one, and 2 with that one. So that's our Lewis dot formula then, okay? Now let's take a look at what the 3-dimensional shape is going to be. So we've got 2 carbon nuclei, and we're going to have the sigma bond in between the 2 carbons. Then we'll have a pi bond stretching at top and bottom here. And then we've got bonds, one of them has to kind of come out toward you. So that's going to be 1 hydrogen. And then we'll need one going back behind everything. Okay, that makes sense? Let's go and label these if you haven't already to make sure we know what the names of the bonds are and what we're going to call them. So the question was that we have 2 electrons on the carbon, they're not bonded to anything. Everything's bonded here. There's not a lone pair anywhere on the carbons here.
But how do you only have 6 carbon instead of 8? Like, why wouldn't you put 2 above the first carbon?
Well, carbons have 4 valence electrons. Is that what you mean? It's not 6. We're not going to worry about the first 2 electrons because they're not in the valence level. Only the electrons corresponding to the position of lithium, beryllium, boron, and carbon are in the valence level.
Right.
Is that the confusion?
Yeah.
Okay. So carbon has 6 electrons, but only 4 of them are in the valence level. Okay. We're only worried about the valence level electrons. All right. So we did the original orbital notation here for carbon. These 2 electrons right here are in the lower energy level. They don't get involved in bonding. Okay, it's only these electrons in the highest energy level that are involved in bonding. Okay? So if that's what the confusion is, then hopefully we cleared that up for you. Okay? So this bond between the 2 nuclei here is a sigma bond. This bond between the 2 nuclei is a sigma bond. This one's a sigma bond. This one's a sigma bond. And this one's a sigma bond. Okay? This is a pi bond, and this is part of the same pi bond. Okay? So, since, if you remember back when we were first started to do S and P orbitals, we said that P orbitals can be designated as being on the X, Y, or Z axis. That makes sense? So we can make sure we're clear that this pi bond is part of the same bond, and the 2 P orbitals are coming from the same axis. We need to call this X, both parts of this, pi X, pi Y, or pi Z. It doesn't matter to me which one you call it. Okay? But that way we can show, since this P orbital from which this pi bond stems, and this P orbital from which this pi bond stems, they are both on the same axis, either X, Y, or Z. Okay? We need to designate this pi bond as either X, Y, or Z. Which one do you want to call it? X. X it is. We'll call this X. Okay? So we'll call this pi X. Alright, any questions about that? Alright, so very often this is described as hot dog and bun. Okay? Like a bun has 2 parts, this is like a pi bond has 2 parts. You got it? Alright, now let's assign you a homework so you don't get this doesn't get stale on you. You can practice some more tonight. That you have. Okay? So our homework then is to write the electron dot notation to Lewis dot formula. The same stuff we've been doing in here today. All right, so electron dot formula to sharing arrangement to Lewis dot formula, and then also the shape, the valence orbital shape for this molecule, nitrogen, oxygen, and chlorine. Please don't think that that's a carbon and an iodine, okay? This is chlorine, all right? That's why you've got to be real careful when you're writing element symbols. If I were writing an I need to put a little bar on the top and bottom to make sure it's clearly an I. So that could be the problem with L's and capital I's and number ones, okay? Sometimes it's hard to tell the difference. So we want to try to be careful about that when we're writing those things, okay?